properties would reorient, and one of its properties is its magnetic moment, and you can drag it around and move it using magnetic fields. So that's really cool, and it gets pretty advanced. But up till now, we didn't say anything much about the orientation of the molecule. Isn't that true? But that's also a thing. That's also important. So we have to add another vector. It's supposed to represent, if you like to do, I really didn't think about the fact that the solution people this year are actually doing the nucleic acids, but I picked an NH because if you were doing proteins, that's what you look at all day long. Whatever. You have a vector, okay? That represents a vector in your biomolecule. It also has an orientation. We have actually 3 vectors. The applied field representing z-axis for all our spin degrees of freedom. It doesn't move. The magnetization vector, which will be controlled by RF and other factors. But now we got the molecule 2, 3 vectors. So the equations we're going to talk about, I just mentioned here, besides magic angle spinning, you might do experiments where you have a liquid, but it's partially aligned. It has a preferred orientation in space. You might have dynamic studies. I think you guys do a lot of dynamic studies. And also anisotropy is crucial underlying driver of many of our structural constraints for solid state NMR. So since a lot of today is going to be building up the apparatus of spherical tensor notation and Euler angles, I just want to know, how much have you actually done calculations with these before, for this class or for some other class? And using? Good, good, good. Otherwise, I have to change what I'm going to do. I gave the person who's helping us with coordination, Whitney, a handout for you for this class. I don't know if you received it yet. And inside that handout are some problems. And you can choose if you like a question and you don't like another question. I strongly recommend the ones on the first line as being kind of more foundational. And then I peppered the lecture with questions also. As you know, we don't really grade you on your homework or something like that. You probably will see some echo of this in the midterm, maybe an easier version of one of these. But these are problems I'm making available in the sense, like, I have thought about them. I have solutions. I think it's useful for you to think about them. It's quite optional. If you're doing solid state NMR for your main research and you hope to read theory papers, if I were you, I would look at all of them. But just, I'm saying maybe in time crunch and you've got other things on your schedule, start with 5 of them. So some of the things we know are different between solution and solid state NMR. It's a funny definition of a solution versus a solid. It's about its correlation time. And if the correlation time of a molecule is slow compared to 100 milliseconds or slow compared to a second, we're going to call it a solid. That's not the same definition you got in middle school. It's also not the same definition if you studied condensed phase physics, but it's our definition. And we're going to call it a nice liquid if the tumbling time is shorter than about 10 nanoseconds. Please notice that there's a gap. I like to call that no man's land. We have a challenge, your generation more so than mine, even though I've come up against this challenge. I've mostly failed. So think about that. Think about no man's land, because there's a lot of biophysics there. And we have any of the wonderful features of NMR in these intermediate correlation time systems. No specific relationship between the molecular weight and the line width is expected for solids. For solution, the tumbling time drives a lot of properties. Aligned samples for solid state NMR are going to show very, very large shifts in couplings, which are orientation dependent, and that's what we're studying today. But even if you align in solution, you get these tiny little shifts, just like ppm. No, not even a ppm. We're going to be talking about things that are like moving by 50 kilohertz, moving by more than the normal chemical shift range. And that has implications for the hardware that's needed for the experiment. It also has implications if these are couplings, not shifts. It has strong implications for how well you have to decouple. So there are experimental requirements that turn out to be different. Nowadays, you order more or less the same instrument, but the accessories will be different, like more power on the amplifier, stuff like that. As they have things that are clear distinctions, they also, solution and solid state NMR, have many things in common. The overall goal of understanding coherent evolution, effective pulse sequences, the prediction of specific observables. This is the same story as what you've been talking about up till now. That we use the same tools even in that pursuit. We have the density matrix, we have the Hamiltonian, we use truncation, we use product operators, we use a lot of frame transformations and fictitious fields, same stuff. Relaxation and dynamics, and even the framework of Redfield theory, Bloch-McConnell equations, etc. We want to get structures from lists of tertiary contacts, and we use very similar computational strategies for that. We face challenges with line width and resolution, even if the determinants of resolution might not be exactly the same thing. So in the end, a lot of it's more similar. So don't feel like we're going to start over or lose our time by moving to solids for a minute. So I want to give you first an example of an anisotropic interaction. I want to remind you how we're going to do rotations. I want to try to write a Hamiltonian that includes anisotropy. And then I want to use spherical harmonics notation and show you how much time that can save. All right, if possible, with you guys this year, once we're done with magic angle spinning, it might not be this week, but I'd also like to talk about some famous pulse sequences and how you would use the standard tools to look at the pulse sequence to write an expected outcome. And I have a couple of favorites, and I would also take nominations. You guys could pick a pulse sequence that maybe you want to write your paper about, and we could address it as a class, okay? So, but minimum for us, if we run out of steam, our minimum goal is to get good equations for magic angle spin. So I picked the chemical shift interaction or chemical shielding interaction as our first example. It illustrates more of the advantages of spherical harmonic notation. And when you can handle the chemical shielding tensor, then it's easy to write the corresponding equations for some of those other interactions that I listed. The only thing that's like, let's say, more advanced than this would be if you had quadrupole. This doesn't cover a quadrupole unless it's really trivially small interaction. And everybody here knows what the quadrupole interaction is. Thank you for being honest. This is very helpful. So we're always talking magnet, right? You have a strong magnet and a little magnet. And actually, you also have an electric interaction between the nucleus and its surround, right? In fact, that would be normally a lot bigger. The ratio between magnetic interactions and electric interactions for pretty much anything is many orders of magnitude weaker for the magnet. So what about the electric interaction? Well, if the electric properties of the nucleus are well summarized by just its charge, then it's spherical, right? The charge doesn't have an orientation dependence. It's just, we picture it as a spherical monopole. And since we're not interested in displacements, we're just always interested in rotations in NMR. And charge, so what? It's not going to cause any rotation. Not going to bother me. But some nuclei, they don't have dipoles, but some of them have quadrupoles. And I'm talking about electric. Okay, magnetic dipoles, sure, but they don't have the electric dipole. It's just a property they don't have. And it's an interesting and deep question to ask why not. But let's not get too distracted, or we'll never get to what we're supposed to. So they have electric quadrupole. Now a quadrupole is something that's kind of like cigar shaped. It doesn't have a plus end and a minus end, but it has a fat axis and a skinny axis. Okay, and a lot of nuclei have this property. And if so, within the context of the molecule, it might have a preferred rotational orientation. So electric quadrupoles do result in rotations of the nucleus. That's going to rotate the magnetic field at the same time then. So we can think about like electric pulses and magnetic pulses. We can think about tension between those two. But for sure, you have the molecule tugging on the rotation preference of your nucleus, and that will lead to an anisotropic shift. If the molecule's this way, move your line down. If the molecule's that way, okay. So every interaction has this anisotropy. I don't want to do quadrupoles because they're more complicated than this. I didn't do dipoles because it's simpler. I decided this was the Goldilocks thing to do chemical shielding. But after we're done with this, we can see how what we built up applies, especially to dipole, which is easier. So what's a chemical shift? Everybody remember what shielding is? Does anybody want to tell me instead of my reading my slide? What is shielding?
The effect that changes how the skin experience, so changes the magnetic field that the skin will experience.
Yeah, it's a local change in the total field. And we think about it in two parts. There is the field you applied, and then there's a response from the molecule or the material. If you're thinking maybe coarse grain, like a bulk magnetic susceptibility, like, I don't know if you ever discussed in freshman chemistry, those gooey balance things and whatever. So there's a bulk susceptibility, but there's also local susceptibility in a molecule. That's what we're talking about. The field isn't the applied field. Generally, it's less. Diamagnetic materials, generally it's less. So what do we say here? That you have a reaction in the orbitals. And one of the reactions is to induce a current, a net current. And so these currents cause local inhomogeneous, anisotropic. Inhomogeneous means spatially different. Anisotropic means rotationally different magnetic fields. They're small. There's no proof that they are linear with applied field. That isn't necessarily true. But when things are small, we can always hope. We can always approximate. So they are assumed to be linearly proportional. The NMR frequency will always depend on the total field. So we have to add this. So it's amazing that we care because it's only parts per million. That's an amazing thing about NMR. So I'm going to sometimes use B naught and sometimes be applied. It is no distinction. It's just if it's the applied, it's because I'm trying to make a point, like say, don't forget, this is only the one you apply. Local shielding fields are induced. The NMR frequency depends on B total. And so you have this equation, right? You've seen this equation before. And these are vectors. Fields are always vectors. I is a vector because we have the measurement along X, the measurement along Y, the measurement along Z. So this is the dot product between two vectors. And this is just a scaling factor. But the important thing for today is that we can't just use B naught. We have to add this induced field due to the magnetic susceptibility. So the shielding, which has a symbol sigma, is unitless. It's unitless, right? Because it's a generating a field. It's just a proportionality constant between the applied field and the induced field. So it's got to be unitless. It is small. It's assumed to be the linear leading term describing the ratio. So a formal definition of it, which could be useful if you were going to get it out of quantum mechanical calculations, is it is the first derivative of the induced field with respect to the applied field. And it's much less than 1. Okay, so the frequency can be written in terms of sigma and the field. Sometimes we're going to be in a rotating frame where we remove B naught. And we want to just focus in on this local field. So in that rotating frame, we're going to be talking about this term. So we might just get interested in just isolating this term and forgetting that it always has to be added to a Larmor frequency. So you'll see that in some of the slides, many of the slides. Some things that you were taught many years ago that I will remind you of. That the frequency, we calculated the frequency here in the last slide. And of course, you could also talk about that in radians per second versus cycles per second. And our spectra, usually we pull out nu. omega over 2 pi cycles per second. But when we have theory papers, we often talk about omega, so don't get confused. So specters of 2 pi, famous stories about people who wrote beautiful, beautiful simulation programs, and they have a mistake of a factor of 2 pi. So chemical shift in ppm, your sample less a reference divided by a reference, and we have to agree as a community who's the reference. Jargon. Shielded means dropping the frequency further, more electron density, more dropping the frequency. So if I'm more shielded, my frequency is always lower. Deshielded means, okay, I was a methyl group, I was quite happy, and I showed up near 0 ppm. Then I'm being measured, and somebody took away one of my neighbors and added something super electronegative, or even more electronegative, or took away 3 neighbors, all of whom were electronegative, and I'm starting to lose my electron density. That is deshielded. That's the concept of deshielded. Okay, and it is less shielded, less electron density, less shielded. And here are some synonyms, and this might just help you at some point when you're looking at papers about chemical shifts. More shielded, larger sigma, lower frequency, lower chemical shift on the right side of your spectrum. And why do we call it downfield? This is like history of NMR, because we used to sit at the same frequency and actually scan the field. Electromagnets, you can scan the field, and most EPR still does this. So if something has inherently, oh wait, this is backwards, right? If it has inherently a lower resonance frequency for the same field, then to get it up to frequency, I have to move up in the field. This is backwards. Just fix that on the slide before we go forward.
Available on the chat.
I just think that, please look at the handout first. The handout is like, am I gonna just seem old fashioned if I say this? The handout is in complete sentences. It's complete thoughts. It isn't just like, here's a noun. And therefore, it's also better proofread, I think. And the slides are just kind of like prompt for me to talk. But if you really want the slides, yeah, I'll upload them. But I really think you should try it. So people just jump around in all of these different lingo. And it is a strange thing that we're putting the lowest frequencies on the right. It looks backwards. So just if you get a little bit dyslexic about it, don't feel like you're the only one. Now, just to mention, we have a lot of tools for predicting shielding, which means you predict shifts, the same thing, according to the last slide. So there are database-based prediction tools for chemists, like in ChemDraw. Most of you have probably used something like that before. They assume linear additivity, so they have a limitation in their applicability. We have database prediction tools that are more like based on machine learning. They're smarter, they're not necessarily always linear. And a wonderful one I would mention is ShiftX for biopolymers, for proteins. We have prediction-based tools based on ab initio or hybrid calculations, like AFNMR out of David Case's. And when you do that, you get the induced field as follows. First, you calculate the current flux. And that is obtained using first order perturbation theory. So the perturbation would be the applied magnetic field, and you have to sum the expectation value of the current operator over a lot of states. So anytime you find out that the prediction you want from quantum mechanics has to do with excited state properties, don't expect magic. Don't expect it to be perfect. Predicting ground state properties is so much tried and true technology and checking and validation and optimization. But I'm trying to emphasize here, this is actually, as much as anything, an excited state property. and therefore challenging. Anyway, once you get those currents, then you use the Biot-Savart law to figure out what the field would be. Now, there's a useful repository for work other people have done in terms of like quantum mechanical predictions of shifts. And there are scaling issues like where is zero, like predictions of the standard compounds that we use for chemical shift references. Like the fact that for some kinds of calculations, when we predict it, we get too much variability in the shift with respect to structural parameters. So sometimes people kind of by hand scale back the effects of the environment. So they get the trends right, but not necessarily the exact amount. And they've noticed that they could just kind of scale their results. So some of this is discussed there. One of the things that these predictions really get right, though, is the orientation of the most versus the least shielded direction. And that's what we're going to talk about next here. So up till now, everything I said, you could have thought I was talking about shielding as if it were a scale, as if it were just like there's a number for that function food. But that's not true. If I rotate the molecule, the shift changes, it's anisotropic, and a scalar can't capture that. A scalar will never tell you that story. So when we wrote that B induced is minus sigma times B naught, actually B naught is a vector and B induced is a vector. And the right thing for sigma to be is a tensor. So vector is rank 1, meaning you only have one spatial index, an index that runs from X to Y to Z. Shielding, and this is to, they're both vectors, right? But shielding is a tensor. It's called rank 2 because it has two spatial components. And if I give it a subscript, I need two subscripts. Because I need to tell you what field I perturbed along, and then what field direction I want to measure along. And that's why it's a rank 2 object. There's a perturbation direction, and then there's a measurement direction. Does that make sense? So if I were to put B naught in here as a column vector, I'd have Bx, By, and Bz, and I'd have to multiply by matrix multiplication methods to get B induced, X, Y, and Z. So I singled out one particular element here, and it corresponds to my cartoon. Z, X component of sigma is the field along Z and response along X. But don't be confused by my cartoon. If I came in along Z, I could have a response along any direction. I'm just reporting one of them in this encirclement. So coming in along Z, I have three answers, right? This one and this one would correspondingly give me how much induced field I would have along Y and how much I have along Z. Should I pause for a second? Is there any comment or question? Yeah.
Should I at this point believe that this structure is symmetric?
No. If I poke along Z and I probe along X, I almost put this on the slide, but then I decided it's too much per slide. What I'm doing, I'm poking, I'm trying to get some electrons going in that high cloud. And then I say, okay, I got some electrons going. What does it matter for the X direction, right? But if I could poke along X, do you really expect anything similar to when you poked? No. But a lot of people treat it as if it is. So that's going to be in 5 minutes. Why are they doing this? It doesn't make sense. Other comments or questions? If I want to literally do some of this matrix manipulation for you just for a second to make it more concrete, I have to remind you that actually B was before sigma. So it would be a row vector. And B, and because I stood after sigma, remember in the equation? So that matrix multiplication, I'll take Bx times sigma 1, By, sigma 2, 1, Bz, sigma 3, 1. And that will be my entry for the resultant first component. Take these three, multiply them with these three, and I get that. I don't know how recently you guys did this kind of math, so I'm sure all of you did it at some point. Right, so then I get a vector, and I should have commas between this, but this is the first entry of the vector, second, and third, okay? In case you happen to study this at some point before, when these kinds of analogous treatments are presented for physics classes, it's usually stress and strain. The idea that you have a force that you apply on an object, but the object is not isotropic. Very few things are. It's hard to come up with an example. Even if you pick like Jello, Jello seems to have like not much going on, right? Everybody know what Jello is? It's sort of culturally specific. All right, so I poke on it this way, the response along Z is not going to be the same as the response along Y, right? It's going to shrink along Z and it's going to bleb out along Y. And that's true for the strains, the displacements, the deformation. It's also true for the internal stresses, like what forces would you feel if you could go inside the Jello or whatever. But it could be even more complicated. If you're talking about wood, wood has a grain, now X, Y, and Z are all different, right? So that's quite analogous to what we're talking about, just in case you happen to study it before. I don't mean to go off on it as a tangent, but now one simplification, we're very keen on simplifications because if we're going to do these calculations all the time, it's going to get tedious. So we have an eye for simplifying these right now. One thing isn't B not always along Z? So does B really have to be this generalized vector, or couldn't it just be 0, 0, 1? Yeah, sometimes. And we'll see why it's only sometimes in a minute. But if that's true, then the three components of the induced field, you get a response along X, a response along Y, and a response along Z. That's easier if it's, applicable. All right, so you got the molecule gave you back a response. You poked it with a B field and it gave you a response along X, Y, and Z. But I'm only going to be interested in the Z component of its response. And why is that? Why do I only want the Z component? Poke along Z, and I only want to measure along Z. Why? Please.
With the direct interaction between the nucleus and the ligand, Riemann Hamiltonian is orders of magnitude bigger than the addition from the other sheet.
Yes. And when it's bigger, what happens?
The bigger parts of this interaction that commute with.
Commute. There's this idea that we only keep the part that commutes. And does anybody accept that or believe that? Or what's your idea about this? This sort of sounds like I've heard that before, but I never really believed it. Look at this. The total field, in that we're talking about it having vectorial components. The total field, which is, at the end of the day, that's what we care about, right? We want all three in principle. But the way we add it up, we have to listen up to Pythagoras. So we have to square this big one. So it's not just because this is smaller than this. It's because when I square it, this is 12 orders of magnitude smaller. I mean, then we don't have the precision. We have a lot of precision in that. So therefore, we could say the square of the total field is basically B0 plus BZ squared. But now notice these guys got it added directly. They don't have to be squared before added because they are parallel lines. It's that simple. It's just the geometry. So truncation is our next simplification. Orthogonal components in the induced field essentially do not affect the frequency appreciably. They're perpendicular and so much smaller. They cause the precession to be tilted, but you can't tell when you make your measurement. The parallel components affect the frequency directly, linear addition. So a question to you about this. We're assuming that By and Bx from the molecule doesn't make any difference. You could take real numbers for a real molecule and check that. I just threw up something super fast and said it's 10 to the 12, but why don't you just take a little bit of a minute? It's really important that you're convinced of this for the remainder of your career in NMR. The RF field is orthogonal, and it is also much, much smaller than the main field. But we know that it does matter. It's orthogonal and much smaller, and it matters. Why is that? Why does the RF field matter if it's along X and it's small?
Even though its magnitude is orders of magnitude smaller, it oscillates at a frequency which is close to the alarm nothing.
It is resonant. It is resonant. That's a really important part of one of the first lectures that Art gave. And if I would tell you to review one of them and your basics of NMR, make sure you've internalized that. And then would the CSI ever matter? The other terms in the CSA, the X and the Y terms from the CSA, would they ever matter? Can we drop them now for all time for the rest of the class, or are there maybe some special circumstances where we have to keep them? Any opinions? What if the molecule's motion was sort of resonant with the Larmor frequency? Then they would be like a little RF pulse. Now, you could actually do that with electric manipulation of the molecule, and we could talk about that more later. But what if the molecule just on its own, you know, it's just the way it moves, it just has some, what they call spectral density at the Larmor frequency? Then it would be a huge mistake to drop those terms. So when we do relaxation theory, we're going to be talking about those orthogonal terms. But today we're just trying to predict the shift, the spectrum, and we should be very comfortable dropping them. Any more questions on that? So that's two simplifications. So we were faced with this whole thing here, which I think everybody knows how to do, and everybody knows enough to know that's going to be tedious. Do I really have to do this every time? It's going to be a lot of terms. But the truth is that we only need to take BZ and IZ term. That we can pretend everything else in here is unimportant. And what that means is that the only element in this 9-element tensor that we're going to make any use of is sigma 3,3. So that looks a lot like our old equation. But before, if we were talking about solution NMR, that was sigma iso. That was the average value over all orientations. Now we're saying if I have a static sample, I just need to know what the susceptibility along Z is when I perturb along Z. It's not the isotropic one. It's going to be some other number. But that's happy that when you only have to calculate one thing, and we want to try to hold on to that advantage in some way. So that's a summary. Okay. But there is this business of the molecular orientation. Let's just talk qualitatively for a minute before we turn to the computational apparatus. Molecular orientation. The actual value of sigma 3,3 will depend on the orientation of the molecule. That means if I manipulate the molecule, I'm going to change these values. Like if I could in real time rotate it, you should see these values coming and going up and down, all 9 of them, but in particular the one we want. If B naught along Z for a carbonyl, because I like carbonyls a lot, say Z is pointing along the perpendicular of that Y aromatic plane, okay? And let's say I want the measurement along Z also. This item here, perpendicular. It turns out that's where you get the most shielded possible value. That's the place to put the molecule if you want the element that's here to come to the lowest number that you ever get for a carbonyl, which happens to be about 100 parts per million carbon. Okay. That sigma ZZ is a general concept, but the shielding for that direction in space for the carbonyl is more of a specific concept, and we're going to call it sigma 3,3. All right, so sigma ZZ could be anything, but when you line the molecule up in that direction, then sigma ZZ equals 105. That's the lowest it ever gets, and it has a special name, sigma 3,3. Now, how about another axis? What if you're in the plane? What if you poke? I don't have a picture for this, I don't think. But what if I took this red arrow and I stuck it in the plane instead? Okay. And then I would maybe choose to put it sort of halfway in between the two oxygens, or a little bit more along the single bond, if there's a difference in bond order. That would turn out to be the least shielded that you could ever get out of this system. And it happens to have a value around 240 ppm. And when you line things up that way, sigma ZZ takes on a special value that has a special name, sigma 11. Most shielded, least shielded. Most shielded, least shielded. So the frequency depends on the orientation of the molecule's axes, which I give numbers. And how does that compare with the field, which we gave letters for? There's two coordinate systems, and how do they line up? I'm going to have to know how to rotate this tensor to express the correct coordinate system to predict the experiment. Let's say a little bit more about I have to rotate it. Well, people used to do this. This is a paper by Hans von Willigen. Was it? I think on not a postdoc, but maybe like an early sabbatical or something like that in Bob Griffin's group, and a couple other authors who are looking at an amino acid, and they grow a single crystal. Okay, and we need two coordinate systems again. We need one for the molecule, and we're interested in axis number 3 here. This is the molecule, has numbered axes. And we also have a laboratory coordinate frame, and we're interested in the z-axis, which is along B9. Okay, these are two different coordinate systems. And how could you explore experimentally how the relationship between those two axis systems matters? Well, you put a goniometer right in your NMR probe. And that's not as easy as it sounds. Goniometers are already very precise. They have gimbal mounts, they have 3 axes. It has to be completely non-magnetic, and it's cool that they did this. It's also very tedious. Not very many people did these experiments. I think while they were in John Waugh's group, there were also some nice experiments from Griffin and Pines. But this was something that they put the numbers in the books for all time, but at some point people stopped doing this because it's just really a labor of love. But you would then get all the different carbons, and they wouldn't be where you think they're going to be. Each one would be at crazy land chemical shift. But then as you rotate the goniometer, each line moves around, and you have to track, if this is Joe, you have to watch Joe when this, you have to be able to figure out how to map them from one spectrum to the other. And then you get to draw these curves through them. One of the things you're learning is if you can compare it to the X-ray diffraction, if you know what the crystal axes are and how you mounted it, you could establish without a shadow of a doubt what is the most versus the least shielded orientation. This is ground truth. Now, I want to talk about if you don't have a single crystal, we get something that we call a powder pattern. And I think of that as a histogram of all the frequencies of all the orientations if you ground your crystal and just put it in the NMR. So again, we need two coordinate systems to talk about this. This would be the line shape, but how do we understand this? Now, again, we have a coordinate system for the molecule, and we have a different coordinate system for the pulses and the applied field and the nuclei. The angle between this Z and this Z has been encoded in a heat map, meaning one extreme angle is blue and purple and the other is red, okay? So that's the angle theta that relates this z to that z. The frequency that you would get at that angle is over here. In other words, this orientation is that frequency. The purple orientation is the purple frequency. The red orientation is the red frequency. There's an equation that relates the two to each other. We're going to derive that. So just don't worry about where it came from, because that's our job. It's coming right up. But I do want you to notice the intensities of the line. The intensity of the line, the lowest frequency, most shielded, molecular axis 3, when it's along B naught or lab Z axis, it's indicated in purple. That's the pole. There's not a lot of space at the pole. So there's not a lot of intensity in that purple bit. The highest frequency on the molecular axis 1, it should say, is at the equator, perpendicular to B naught. And that axis, that orientation rather, oh no, I guess it's right. I don't have to fix it. Never mind. Just say that again. The highest frequency comes when you take that same molecular axis, but instead of putting it along the pole, you put it in the equator. So axis 3 gets placed in the equator. That means that theta is 90 degrees, and there's a lot of space at the equator. So when you go to these orange-yellow frequencies, you get a nice tall peak. This is a powder pattern, and when you predict it quantitatively, a cake pattern for the person who first wrote the equation for that line shape. The example I just showed you is what I would call uniaxially symmetric. That means that X and Y are indistinguishable. It has only one unique axis. Axially symmetric, uniaxially symmetric, synonyms. Cylindrically symmetric, this all means the same thing. Now, X and Y are not the same for very many things in biology, because we're just completely peppered with chiral centers, and then you're not going to have X and Y be the same. So let's look at an example where X and Y are the same on the top versus are not the same on the bottom. And in a general sense, the molecular symmetry expresses itself in the characteristics of the tensor. If the molecule is axially symmetric, the tensor will be axially symmetric. It's the electrons, right? And the rhombic or asymmetric tensor has 3 turning points. Sometimes people use that phrase. So it has a left edge, left shoulder, right edge, right shoulder, and a peak. The uniaxially symmetric tensor has just the 2 edges that you could report and you could compile, and you would do that in parts per million relative to a reference compound. Those features always correspond to unique axes in the sense of the symmetry of the molecule. So we can have good chemical intuition and guess which way they are. If you have aromatic character, you could do a good job just guessing that you want to be perpendicular to that to get the most shielding, for example. And as I mentioned, if you have access to quantum chemical calculations, the directions are almost always right out of that, even if the values aren't perfect. Now, just a minute for some conventions. I've been using what might be called IUPAC rules. So you number them 1, 2, 3, the chemical shift of 1 being highest, that is the frequency the highest, or the shielding the least. And then they're monotonic like that. So 3 will always be most shielded or lowest frequency, okay? That's IUPAC rules. Many papers published in like ACS journals will have IUPAC rules. But somebody named Haberlin proposed a different convention, which is elegant and compact. And that is as follows. ZZ, okay? Now, don't get mad. I know we were having the laboratory frame use XYZ, and we only had 1, 2, 3 for the molecule. But the Haberlin convention uses X, Y's, and Z's for the molecule also. So then you'd have to have an X and an X prime and things like that. Haberlin says the Z should be whatever's furthest from the isotropic, but it could be higher or lower. Could be either way. It just depends on the properties of the electrons, okay? So Z is whoever's farthest away. X is the next farthest one, and Y is the closest to the isotropic. The isotropic, by the way, and I don't think I said this already, is always the simple average of the three numbers. So if it's axially symmetric, you take the average of Z and 2 copies of the orthogonal one, okay? So that's really important to know, that if you already know the isotropic from some other measurement, then you're really only looking for 2 fitting parameters when you look at these line shapes. 2 new pieces of information, because you already know the isotropic. Then there's another parameter besides the isotropic shift that's a really handy linear combination of the 3 values of X, Y, and Z, and that is sometimes called delta delta. Now, the reuse of symbols is quite something for NMR. I mean, delta was already the right value, right parameter for the chemical shift, right? But with this capital delta in front of it, it's a handy parameter characterizing the width, and we call it the anisotropy. How anisotropic is this system? Fatter width, more anisotropy. Put a number on that. Here's how it goes. DZZ minus the average of X and Y. So here's the average of X and Y over here in a graphic, okay? You see this red thing between X and Y, that would be its average. And we're asking, what's the distance, delta delta, or the reduced, or sorry, the anisotropy. We're asking for the distance between that average and the Z. And that somehow characterizes how anisotropic the system is. But it is scaled, as you might notice, by 3 halves. The formal definition of the anisotropy. So, or is scale, sorry, I just said that a little bit wrong. You don't scale this expression. This is delta delta. But you can think of it as a scaled version of what is sometimes in the literature called a reduced anisotropy. So you're going to see both of these symbols, delta delta and little delta, in some of the theoretical expressions coming up. And they tell you the same story. One is a scaled version of the other. Does that make sense? I just misspoke a second ago, so I just paused for a question. Now, the third parameter will give you a hint as to whether X and Y are the same. It expresses the difference between the X and the Y direction. And it is symbolized by the Greek letter eta. Its correct term is the asymmetry. And you take the difference of X and Y, and then you divide it by the difference between Z and iso, namely the reduced anisotropy. Eta is unitless. The anisotropy has the units of chemical shift. The isotropic shift has the units of chemical shift. Okay, these are just conventions. You can look at them more later. Yeah.
How do you see terms like span and skew?
Yes, span will correspond to, I think, a scaled version of the anisotropy, and I have to double check to know what's the factor. And skew is another expression for the asymmetry. Let me double check so I don't put something incorrect out there. All right, so just contrast 3 experimental formats. Liquid state NMR. What are we measuring? The molecule is rotating rapidly on the time scale of the measurement. So you know that you're digitizing your FID, the time between one point and another in an FID is what order of magnitude? Roughly how long is a time between you? Like I'm talking about within one FID and you take two different digital samplings. How long would you imagine is in between those two data points? Is it a millisecond? Is it a microsecond? Second? Your FID, you're taking digital points. Yeah, 10 to 100 microseconds of this order. There's some interesting systems where you should turn it all the way down to 1 microsecond, but we don't do this very often, right? So in that time, in the time of 10 microseconds, your molecule has tumbled 1,000 times its characteristic time for sweeping out the sphere. It has sampled everything. So in the solution NMR experiment, we have averaged all orientations, and we expect to measure sigma ISO. In a static NMR, you take your powdered sample or just randomly oriented protein or whatever, you expect to get these powder patterns, but if you have several different carbons that overlap, they're not going to be so sharp. And maybe you have some couplings that we didn't mention yet. So they tend to be kind of ugly line shapes like this. And what we're going to talk about is taking that same sample and applying magic angle spinning. So now you didn't dissolve it. Now it's still static, but what you're going to do is macroscopically rotate the whole sample in a deterministic fashion. And it will be rotated at a particular angle with respect to the applied field. That's where we're going next. Now, before we do that, I just want to mention one other thing, that the information in the three tensor values is almost always much more than if you just had the one tensor value. I mean, as a chemist, like to interpret it. We see the chemical shift and we reach certain conclusions. We say, oh, it must have an electron withdrawing group or whatever. So for the biological systems, we look at these chemical shifts and we might say that's an unusually strong hydrogen bond, something like that. So you can look for compilations of chemical shielding tensors of certain functional groups, and here for carboxylic acids and carboxylates, here for the amide carbonyl. And there are clear trends that mirror trends in infrared spectra. Infrared spectra for many, many years were believed to follow what? The hydrogen bonding environment, the so-called Badger-Bauer rules. So this is saying that the chemical shielding tensor also follows a hydrogen bonding. But the interesting thing is that information is coming from one particular tensor element, the middle one. Now, we measured 50 compounds to get this compilation, and that for sure there's a little hash here. That's not a perfect correlation, but also one of the tensor elements is nearly invariant through the series, and the third tensor element, the most shielded, perpendicular to the aromatic ring, is discretely different if there's a proton attached or not. You can't piece all that out of the isotropic value. If you plot the isotropic value for this series, which we did, but it's not here on this graph for some reason, it's hardly any different. You go down all of these compounds and it's like, my God, it's moving by like 1 ppm and it's got a lot of noise in it. But here you can say yes, no, is it protonated? Yes, no, is it a strong hydrogen bond? And if it were moving so that you were getting tensor characteristics that were motionally average, you would know because this one would move. So it's like so much information, right? So all this complexity that we're about to address, this is a similar kind of story for the nitrogen shielding tensor for amides in a protein. This is for the C alpha and asking questions about secondary structure of that carbon. So is it in a sheet or a helix or whatever? So that's a lot of information. Another thing that I'm only mentioning, and I don't think we'll have time for in this class, but this orientation information is utilized in experiments where you align your sample, for example, a membrane protein in a planar bilayer, and you know the overall orientation of the helix. when you make the measurement of the chemical shift or a dipole coupling, you learn the orientation of one particular nitrogen-hydrogen bond within that helix. That's bold. That's great. Right, so it's going to be a little bit of a pain to do what we're about to do, but I just wanted to emphasize how much information there might be. So let's just start a little bit today, the theoretical expressions for anisotropy. So we're going to try to write an expression for a Hamiltonian, for a frequency that includes this degree of freedom for the molecule. We need to choose a coordinate system. I like to say the Hamiltonian has no coordinate system. It's a scalar, it's an energy, it's a number. But the ingredients we're using to construct it absolutely have a coordinate system. And we need to pick one. They need to be written consistently, self-consistently. Like the vectorial spin operators, they have their preferred coordinate system. They like to be in what we call the laboratory frame, where Z is B naught. The tensor describing the molecule susceptibility, it likes to be written in the molecular frame. And in fact, if you go get one from the literature, from someone else, they're going to give it to you in the molecules frame. They can't give it to you in your magnet frame. They don't know what you're going to do when you place the molecule in them. They have to give it to you in the coordinate system of the molecule. But we need to write our Hamiltonian. We stay in the same frame all the way through, right? Now we just look at the thing on the bottom. The Hamiltonian can be written with everybody in the lab frame, and you should get the same answer if you write everybody in the frame, coordinate frame of the molecule. You should get the same answer. There shouldn't be any difference. It's a scalar. But what you must never do is write spin degrees of freedom in the laboratory frame, where that's easy, and the molecule's response in its coordinate frame, where that's easy. That will give you nonsense. All right. So it becomes clear that what we need to do is to convert reference frames. That's the job we have to do when we predict spectra. Like here, you know, this is a coordinate system for the molecule. We mentioned this already, but just to put it up one last time. Sigma 3, 3, perpendicular to the y aromatic. Sigma 1, 1. So we know their values and where they point. So we like to write the spin degrees of freedom the blue way here in the laboratory frame. We like to write PAS this way. But we have to find some kind of happy compromise and rotate somebody. So what we're going to do is rewrite the vectors, because tensors are somewhat new. Don't want to assume everybody knows how to rotate a tensor. So what I'm going to do is I'm going to use this equation, and I'm going to rotate these. I'm sorry, I meant to say I'm going to use the middle equation. And that means that my work is to take the way I know how to write this in the lab frame and rotate it into the principal axis system, because rotating a vector is something we should be able to do. So we're going to move the vectors B and I into the principal axis system. Everybody with me? That's our goal. So I'm going to go quickly through this, but there's no shame in needing these slides, these first slides. If you want to build this up and you haven't looked at this in a long time, I wrote out some stuff for you here. This is like, if you have a vector and it's just in a plane, it's just in 2 dimensions. You know how to do this with matrix manipulations. You definitely know how to do this. So you've got some vector and you want to express how it looks differently. Your vector is a column, and it's X and Y, and you want to say, after you rotated it, now what is it? And the thing you do to it is you apply a rotation operator, and your vector is a 1x2 column vector, and therefore your rotation matrix is definitely going to be a 2x2 matrix. And its entries have to be cosine theta, minus sine theta, cosine theta, as written here. So you, if you need a review of this, just think of this. Think of a vector along X. That would be encoded as 1 on the top, 0 on the bottom. Okay, that's a long X. And say you're going to rotate it by 90 degrees, so you know what to put in here. And then just do that manipulation, and you should get a Y vector rotating, in this case, around Z, right? The rotation axis is perpendicular to this plane. All right, you should be good with that. But I want to point out something, two details. One is that there's a little difference if you're going to rotate a row vector versus a column vector. And we're doing both in this case. So this was a column vector. This is a row vector. The expression is slightly different. Okay. So we need to do a different operation on U. There shouldn't be a prime. So what we do to U is, yeah, we apply R, but we apply it on the right to return another row vector. And also we don't use R, we use R inverse. And anytime we need the inverse of a simple matrix like this, we're going to swap the off diagonal elements. Equivalently, we can change the sign of the angle. Okay, but the column vector is this format, and the row vector is this format. Don't forget that. But what's even more important for us, and makes everybody feel a little dyslexic for a while, is we also have to say out loud, be conscious of whether we're actually trying to move vectors or are we trying to change the coordinate. Because most of these problems, we're trying to change the coordinate frame. You should notice that it's not quite the same. The coordinate system is rotated by an angle theta while the vector is sitting there, which is going to be the case here. We don't want to move the magnet, right? We just want to change coordinate frame on it. That is called a passive rotation or a frame change, and we write the apparent vector positions in the new frame. If the frame itself involved, like going from the lab to the principal axis, involved rotation by theta, then rewriting everything will be unwinding that by minus theta, okay? Does that make sense to everybody? I got a vector, he's sitting still. First, I like to look at it where Z was like that, or let's say X was like that, parallel to it. But now I want to change the frame, and I'm going to go counterclockwise. That means my vector feels like it went clockwise, right? Same rotation, opposite angle, or you could say R inverse of the same angle, either way. So for the column vector, passive frame transformation, it's the same as we talked about before, but a change in sign. Now, those are just reminding you of the rules in 2 dimensions, when you have column versus row, when you have passive versus active, not in 2 dimensions. Okay, so we need to rotate something in 3 dimensions, and that's where these Euler angles come in. And you can do it a lot of different ways, but you're not going to do it all with one angle. And so we have to agree on a convention. Let's say we take a baby case, an easy case, where everybody's uniaxial. The shielding interaction is uniaxial. And by the way, our magnet is uniaxial because we haven't done anything that distinguishes X from Y in our magnetic field. Then actually it is just one angle. It's the polar rotation from the old Z being Z along the B naught field to move it to the Z axis of the crystal. Nobody cares where X and Y are. You can just get away with one angle. What is that angle? Formally put, it is the arc cosine of this dot product normalized. Okay, so we want the angle whose dot product, whose cosine looks like the dot product of the 2 Z vectors. Feel free to look at that and come back with questions about it, but that's the right expression for the angle you need if it's all a uniaxial problem. But what if it isn't uniaxial? Because we're going to be interested in chemical shielding tensors, and they are not. They are not uniaxial. So generally, we need 3 angles then. And remind yourself, like this is not the Rose convention. This is not Euler angles, but this is something that might just ring a bell for some of you. You know, if you have a completely arbitrary shaped object with no symmetry, or, no equivalence. It doesn't have a symmetry axis, but it doesn't have an equivalence between the three Cartesian. Then, we talk about roll being different from pitch, being different from yaw. So we know we're probably going to need 3 angles. The way this is constructed for Euler angles is the following. We're going to build everything around that center piece of moving the z-axis from the old position to the new position. That's the most important angle in many respects. So the center rotation will still be a rotation specifically about y through a polar angle beta. So we're not going to use x. This is a convention. We could have, but we're not. We're going to use y. So here is a y-axis, the one called n here. Pay attention to n. N is a mutual perpendicular for the two z-axes. So here's z, old z. So in our case, that would be the B field. And here's the new z. That would be the z for the crystal, the molecules, symmetry axis. We need to find a mutual perpendicular for those two. His name is the node line, n. And for a little while, that's our y-axis in the middle of the problem, okay? So if I rotate about n through an angle beta, I move old z to new z. That's the crux of it. However, I think about it this way. I got to set myself up to get my y there. And what I do, here's my old z, and here's my old y. Both of these two are perpendicular to z by construction. So step 1 is a rotation around my old z to move y to where I need it. Then I rotate around the node line and I move my z. And then at that point, I might need to move my y to the new y, which could be a rotation around the new z, because the new y and the node line by construction are both perpendicular to z. You don't always need to do that third step, because now you're in the magnet, or whichever side of the problem that you're in the magnet triangle, you may or may not need to do it. But let's, for completeness, include all 3 of those steps. So one is the setup to move from old y to the node line. The next one is move your z from the old to the new, the major axis. And the last one is move that node line over to where y really is. 3 rotations. A question for you to think about between now and, because we usually stop by around now. Oh, okay, good. A question you can think about anyway, we won't do right now, is how can we affect a rotation around X? So this was a story of rotating around Z, and rotating around Y, and then rotating around Z. How can we do an X rotation with this formalism? Just something for you to think about for next time. So if I wanted to write out these Euler angles with the Rose convention, here's what it would look like in 3 dimensions. A rotation around Z looks like this. You do nothing to the Z component. So Z mixes with nobody but himself, just preserve. And then X and Y, well, we already looked at that. That's a rotation in a plane, right? This is the actual rotation around Y that moves your Z axis for you. And then this is another rotation around the final Z. So it's like a sandwich of 3 rotations. And if you actually multiply these to each other, you get this ugly thing. And that's what we're going to be doing all the time if we don't learn spherical harmonics and their wonderful simplification properties. So that's what it is. R from one system of coordinates to another is our Z at alpha, then our Y at beta, then our Z prime gamma, and it gives you all that hash. So for our chemical shielding, what did we develop that for? Because we wanted to move these guys from the lab frame to the PAS frame. So we're going to try to write this thing that's in red. And in place of this, because we don't know what that is, we don't know what B naught and the PAS is, we're going to substitute in this expression. B naught in the lab, which we know perfectly well what it is, times this rotation matrix that we just developed or described. And we have to do the same thing with I for the PAS. Now, in these two paragraphs here, I'm a little bit sweating the details. So our lab to PAS would be the rotation that moves the coordinate system from the lab, where we know how to write things, to the PAS through an angle, sometimes given by capital omega, of course it's used for other purposes in NMR, and it's also alpha beta again. Okay. But note, please, that if I rotate from the lab to PAS by omega, that is the same as the inverse rotation from the PAS to the lab by omega. So you can always substitute these happily back and forth. Recall the active rotation of column vectors is this. Passive change of a static vector, therefore, is that. So I'm just kind of going through the sign conventions here for you, and feel free to kind of review that at your leisure. But when I do that sub, I say IPAS is R times I lab, and R for what? For the active rotation of PAS to lab. B naught PAS is written correspondingly. And because it's a row, not a column vector, we have to use the inverse and multiply after the vector. So I just sub those in, and this is the proper way to write a Hamiltonian for an interaction that is anisotropic, whose values are known, and whose angles relative to the field are known. You got to know all that stuff or you can't make any use of this. That's the expression. Now let me point something out. If I take the same exact equation, but instead of grouping this together as a chunk and this together as a chunk, I say, let's think these guys are in the lab, and I'm going to group all of this together as one chunk. Okay, my values from the literature for the shielding, and then my rotation matrix that I somehow know for the PAS, I somehow know how I placed it. It would appear that this sandwich of three matrices is the right way to write the PAS in the lab frame, and that is true. This is the way that we should rotate a tensor. Have you done this before for something? Rotating a tensor in this way? So a tensor being a second rank object, it has two spatial components, two independent spatial components. One copy of R won't cut it. It needs two copies of R to get it rotated because it has two indices, because it is rank 2. So it's called a bilinear rotation. So you need to do this whole sandwich to rotate a tensor. And if we have more than one tensor in our Hamiltonian, each one will take, for a coordinate frame transformation, it will take this kind of an approach, this bilinear multiplication by the rotation matrix, okay? So it's not going to behave quite the same way. Maybe some of your intuition won't work on a tensor about like what will happen if I rotate it by 90 degrees. Maybe you'll be surprised by what happens because you're multiplying it by this matrix twice, not once. Make sense? That's a really important piece that we just got to. In NMR, we often use what I call nested frames. We don't just have the lab and the PAS that we think about. We think about maybe the principal axis system gets dynamically averaged. So then maybe we should have another frame that represents when it's after all that averaging. Maybe it have different orientations, definitely have different values. Maybe for that one interaction, we need to place it into a crystal because we're going to have more than one interaction and they all have to be joined together in one crystal. So we'll have something called a molecular or a crystal fixed frame. That's like if I had to have the dipole coupling and the CSA, or I had two CSAs for two neighboring units, and I'm going to talk about their interactions, so each one has to be brought together into a common frame. Now, that common frame needs to be placed in a rotor. The rotor is yet another frame. It's not the crystal frame, it's a different thing because it's going to move over time. And this placement of the crystal in the rotor is what's going to build up the powder pattern, because we're not going to place one crystal, we're going to place a whole bunch of them. So these angles, we think of as an inhomogeneous sum of different choices here. Finally, the rotor needs to be converted to the lab frame because that's where the measurements really made. And that's where the time dependence is, right? So you build your powder pattern here in the second to the last step. You do your time dependence of MAS here in the last step. And these, it depends how much you really need these other two at the beginning. Depends on the complexity of the problem. Nested frames. So can you imagine if you have to do that over and over and over again, and R is really a 3 by, I mean, this is a job for a computer. We're not going to have paper and pencil homework that way. This is just what I said, except you could read it. So each of these steps is all of that. Now, by the way, I just said it was sort of like a mystery how I would know those angles, how to locate the PAS within the crystal, how to rotate the rotor to the lab, that we know. Rotors rotate around the z-axis of the rotor. So the rotor frame has a z-axis along the long axis of the rotor, and we need to move that z-axis to the z-axis of the magnet, but also the x and y of the rotor advance according to omega RT. So you're going to have a z rotation, omega RT, and then just single, not time dependent, y rotation to take the rotor up to the lab. So we know what this is. We can write that down. The crystal fixed frame to the rotor, I told you already, those are quasi-random. You get to just pick random stuff and build up a powder pattern. So that's not that interesting. But the PAS to the CFF, that actually, there's a right answer, and there's only one right answer. You have crystal axes ABC that the crystallographer can tell you about, get from a database. How do you know how principal axes of your interaction relate to the crystal axes ABC? And when you do simulations in general, that's going to appear in your simulation and you have to get it right. So you get Cartesian coordinates for the key bond vectors in your functional group. You can get that out of the image structural database. You might be able to just make it up for some cases. You use these vectors to obtain unit vectors for the principal axis system. Here's an example. We know that sigma 3,3 is perpendicular to the plane of carbonyl. So I need a vector that's perpendicular to the plane of my particular carbonyl. What I'm going to do is I'm going to literally take the CO bond as a vector, just get the coordinates of the atoms and subtract them, get the other CO bond. Now I got these two vectors. Now I'm just going to take their cross product. And now I have a vector that's perpendicular to the plane. So just by construction, that will be the ZZ axis. Now you have a vector in the frame of the crystal that represents the Z axis. And you can do the rest of them like that. Like somebody told you in a paper that the y-axis is along the CO bond. So just take that CO bond. Now the third one has to be the mutual perpendicular of those two. So you just take a cross product again, normalize all your vectors, and you're there. That's your coordinates for the PAS sitting inside the CFF. And again, you're going to need that if you want to represent motion of that, or if you want to represent how that CSA might interact with a dipole coupling, you need to do this work. And it's a little, if you do it by hand, it's just a little bespoke. Like each case, you got to pick it through and just figure it out. There are programs like Simpson that will do that for you. So you provide certain information, maybe the coordinates, and it will be computed for you, these rotation matrices. Then if from those vectors for X, Y, and Z of the PAS, what you really wanted was alpha, beta, gamma, then you just do this work. You say, okay, we already mentioned that beta is the computation given here. It's related to the dot product of the old Z and the new Z, and so on. You can have a similar expression for gamma and alpha. So you can do that, and it's a multi-step process, or a program can do it for you. Okay, does that make sense? So those angles, I made them sound like they're magic before. There's a process. There's a good process. I don't think we need that. I think we already talked about that. So where we're going to go next, not today, how do we simplify all these rotations? How do we simplify all these rotations? There's a number of simplifications that we can make, but basically, it all involves using spherical harmonic notation instead of Cartesian. So that's sort of our next topic, is how do we write those rotations in spherical harmonic? And it also does mean that we have to write the shielding tensor and the field and what we call the vector representing the measurement operators, Ix, Iy, Iz, but all of those also have to be moved to a different notation, spherical harmonic. And the motivating idea is what you just saw, that if you have more than one frame transformation, and each frame transformation is that somewhat complicated 3x3 matrix, you're doing a lot more numerical manipulations than you do. It's quite palpably a problem if you're going to do it paper and pencil for homework. But even if you write code, you're just doing stupid things over and over again if you do it. So we're going to look at what exactly is the spherical tensor notation and why does it save you so much time? And do a couple of problems maybe. I think this is in the homework. Do it in the Cartesian and then do it in spherical. Just see the difference of how much time it takes you. The real motivation for me to include this, we could just derive magic angle spinning with a Cartesian and be done with it. And that probably would have fit into almost into one lecture. But you're going to go read papers and they're all going to be using spherical tensor. And you're just going to feel like people are snowing you when they're not explaining it well. So that's why we're going to do this tomorrow. Now, normally you have a problem session now, right? Do you want to take 5 and just see if there's anything you want to discuss, either from today or from something else, or maybe just have a little look ahead to what's coming up next? It'll help you study a little bit between today and tomorrow. Do you have any homework that you wanted help with? Or any questions, like from what we already did? You can't really do the homework for my section already. But maybe if we take part of the homework period and just go look a little further into the deck, then maybe you'll be able to start on the homework. If that's okay with you guys. I know it gets a little glazed over after this much time. So I think you should minimally stand up and stretch or something before we continue. This way you could have a glimpse at the spherical harmonic, and then if you see it again tomorrow, you can start to get a feel for it and have your questions. By the way, the very next slide is the answer to your question. So that should motivate you to stay for 2 minutes about symmetric versus anti-symmetric. Very next slide. You know, this happened also in the other class. You ask a question, I say, oh, you have to wait until the end of the day.
I think it was the same point where lens and skill were talking about.
Yeah.
Same exact.
Yes.
Yeah.
But I felt that they kind of talked around it and didn't go right to the point, which is like, it's a really important question and we should go right to the point.
Right. But usually you pick out the asymmetric and the symmetrize the matrix.
Yeah.
Get the part that has the trace.
And what?
Right.
And what? Yeah, I think when the first time I taught this, it was not for this class, it was just for the group. We used to have NMR theory discussions for our group, which was good and bad because I don't know if I was that overworked or what, but I used to make people do it on Saturday. So that was the best. But it was good, and we did it every week for years, you know? And that's what I developed this for, because I realized everybody stumbles on this.
Yeah.
Is there any physical intuition? Like, that seems like completely arbitrary. But you can say it very, but why are you making? So, I think there are very few experiments where this inaccurate assumption is really making a difference. Very few. It's hard to find them in the literature. Normally, it has to do with situations where you're multiplying two different interactions. So usually we add them up, like each one is a shift, linearized, and we just add them up. But there are examples where you might find yourself multiplying different interactions in a Hamilton. For example,
Relaxation.
it's still an addition.
Oh, okay.
If you have a coupling between two things, okay? And one of them is big enough. So you have a dipole coupling, that's the main Hamiltonian we're going to talk about. But the guy I'm coupled to is a large enough spin that when I change it from X to Y to Z, it might actually change its size. So normally, if I rotate my molecule, it's there. These two magnets stay the same size, I'm just changing the rotation of work. But there are examples where something is that polarizable by the field, that big a magnetic moment, that if I rotate, I also change the size of it. And that is like, kind of like multiplying a dipole times a CSA. So, yeah, unpaired electrons is a good example of that. It's no longer second rank, now it's going to be fourth rank, there are four stations. And how does this relate? Because,
Asymmetry of the.
yeah, and I think that once you multiply them, you're not allowed to drop as many terms. Some things end up back on the diagonal.
So that becomes positive, paramagnetic.
Yes. Very cool area. Okay, some of you didn't even stand up. If you fall asleep, you only have yourself to blame. You didn't even stand up. Okay, so remember that we knew that we had some simplifications that we could in principle make. The two things that we knew is that we're only predicting spectra. B naught always comes along one particular axis, Z, and the measurement always comes along Z. So we knew that somehow we have 9 numbers when we rotate, but that we only really need one of them. But the way we're going about it, we can't just erase the rest of them. That doesn't work in matrix multiplication. You're going to get nonsense if you do that, if you just erase the rest of them. They all matter, even though you're only going to pull that last one, especially when you're ganging up multiple rotations. You just don't have any justification for getting rid of the things that in some sense, you know, you don't need all of it. So what we want to do is untangle that, untease out the things that are going to be in the observable and get rid of the numbers that don't matter. But we can't do it just by saying, I don't really like the 2-3 element. That's not going to work for us. So here's the first step of that. We mentioned already that the chemical shielding tensor is not symmetric. And let's define symmetric here for the tensor properties. 9 arbitrary numbers. If I symmetrize it, it means that I average across the diagonal. So the 1-2 element is always the same as the 2-1 element in this symmetrized version. In order to reconstruct the old tensor, not to just get rid of information, I then would have another piece which is simply the difference between the true tensor and the symmetrized version, which I call the antisymmetric portion of my tensor. It's not 0 for CSA. It is 0 for some other interactions. For example, the dipole coupling is truly 0. But for CSA, it's not 0. So what does this matter? One more thing. It says here traceless one more decomposition. Is it on the next slide? Maybe I have a slide to explain it, or maybe I'm just missing it here. I don't have a slide for it, so I'll just say it without it typed here. That this symmetrized tensor, it has a trace. Everybody remember the trace means you average the diagonal elements? And it might be useful to take that out. So the way I would take that out is calculate sigma iso, which is 1, 1, 2, 2, 3, 3, add them, divide by 3. And take that out. That would be a matrix with only that number on the diagonal, all 3 positions of the diagonal. And then I'd have to correct this diagonal. This would be sigma 1, 1 minus sigma iso, sigma 2, 2 minus, and then this would become traceless, right? If I did that, if I pulled that out as a third term, which should have been on this slide, and for some reason I didn't. So then I'd have 3 terms. I'd have traceless, symmetric, antisymmetric, and then the unit operator times the isotropic shift. That's a decomposition of my matrix into 3 pieces. But for now, it's just shown as decomposed into 2 different. Now, why is this useful? That I took it apart, symmetric versus antisymmetric. It's for this reason. If we know we only want the 3, 3 element, so that means if I need to rotate from the principal axis system to the laboratory frame, I need to apply R twice in this sandwich, like I've shown, and then pull the 3, 3 element. I could think about doing that on the symmetric and on the antisymmetric. And because the antisymmetric, oops, like the other way. Because of the form of the antisymmetric, not just because it happens to have a 0 here at the moment, but because of this antisymmetric presentation, you can show that no matter what R is, I'll never populate the 3, 3 element. It just, you don't get it out of an antisymmetric tensor. And instead of showing you this with pages of algebra that you probably wouldn't want to read, I asked you, just try confirming it yourself. It's pretty easy, okay? So that means that the laboratory frame 3, 3 element for any arbitrary matrix with no special properties can be derived from just the symmetrized. But it doesn't mean we really think it's symmetric. We don't think that. Make sense? Now that hasn't saved us that much time, but I see a glimmer of an idea there. I'm thinking, oh, pull out the isotropic shift, pull out the antisymmetric stuff. Now I'm left with a really funny matrix. It's traceless, it's symmetric. Does it have any special properties that I could make use of that would save me time computationally? So even though it's not, we're going to treat the Scheele tensor as if it were symmetric. That means it's diagonalizable and traceless. So the 3 diagonal entries are the 3 spatial directions on the functional group. So I just jumped over something. Maybe you recently thought about this, maybe you didn't. As soon as it's symmetrized, it's a very easy work to diagonalize it. And once you diagonalize it, you're just going to have 3 numbers. But if it's traceless, in a way, you only have 2 numbers because you know that it adds up to 0. So this is very elegant. You have either 3 if you didn't take out the trace, or 2 numbers on a diagonal. And those actually literally correspond to these 3 numbers. The diagonal form of your symmetrized tensor is the 3 turning points. The max, the min, and the most probable in the powder pattern. So you can represent the CSA with 2 or 3 values, depending on whether you want to move to a rotating frame where the isotropic shift is defined as 0. So you can diagonalize it, always possible, and then you publish those diagonal forms using the conventions we talked about, eta and delta or delta delta. So this is just a recap. Matrix is always decomposed in terms of antisymmetric, isotropic, and traceless symmetric. And the traceless symmetric is where the orientation dependent comes from and could be summarized with just two numbers. Now, there's a better decomposition than that. That was useful to do. It makes you see the relationship to experimental data very clearly. But let's take a step back and see what this reminds us of. The isotropic piece that we might pull out if we decompose it into three, which I think is done in the handout, that doesn't change if you rotate it. If you have an isotropic value, its representation as a matrix is just the isotropic shift times the identity matrix. The identity matrix is the matrix who never changes when you rotate it. So I don't need to rotate it. It's interesting to know it. It should be in some sense a reference frequency for these problems, but I don't need to rotate it. I don't need to do any math on it, okay? Then I've got another piece which is not spherically symmetric. The antisymmetric thing is not spherically symmetric. It behaves in a sense under rotations like a vector. Antisymmetric is vector-like. And you could say in terms of quantum description of other problems, such as the orbitals, that it's like an L equals 1 system. It's a vector, it's like a p orbital. And this is like an L equals 0, like an s orbital. And the part that we need to wrestle with is like an L equals 2, like a d orbital. It is symmetric, but it's not isotropic. It needs to be rotated. It rotates like a rank 2 tensor. So it has funny rotation properties. Let's be a little more formal about that then. Let's think about the L values for these three parts of the tensor. L equals 0, L equals 1, L equals 2. So if we broke down our arbitrary matrix in that way, that's the first step towards a spherical tensor basis set. And the tensor, instead of being 9 numbers, sigma 1, 1, sigma 2, 2, 2, it's going to be 9 of these. The tensor component, you have to tell me what L is, and then you have to tell me what M is. And there'll be 9 of them. 0, 0, and then L equals 1 has 3, and then L equals 2 has 5 examples. So there'll be 9 of them, and you started with 9 independent numbers, you end with 9 independent numbers, but here they have almost a physical meaning. So L for us runs from 0 to 2, because we're only doing these second rank tensors. In NMR, there are higher rank tensors, but we're just doing the second rank for this class. When L equals 0, we know we're talking about something that doesn't change under rotation. L equals 1 should behave like a vector, and L equals 2 should behave like a second rank traceless symmetric matrix. The M values always range from minus L to L. This is just like the orbitals. And they do directly refer to the orientation of the object in space, the projection along Z, or the orientation in space. But when you rotate, you're not going to change the L value. This is not possible to change by rotation. You cannot turn a spherically symmetric object into a dipole by rotating. So rotations always preserve L, but they might mix the values of M. They might change M when you rotate. So think of a rotation as something that will change M, not L. So if I had an arbitrary matrix and it had those 9 numbers, so these are the 9 numbers, M sub something or other is one of the 9 numbers. This spherical tensor decomposition can be thought of in the following way, that the 0, 0, T0, 0, or here I'm using M0, 0, I take the trace and I multiply it by the unit vector. That's my first spherical tensor component. My second one would be L equals 1, but M equals 0. And here's something I derived and maybe needs to be double checked, but you take a matrix of this presentation. It is antisymmetric because all of the L equals 0 look antisymmetric. It only has entries here, and their values are that in relation to the original 3 by 3, and so on. So the m equals 2, you can see that they are all traceless and they are all symmetric. And the amplitude that you would have if you're re-representing something you already knew the values of as a Cartesian, they all will have these prefactors that you could get from those 9. So this is a different basis set for rewriting your 3 by 3. 9 linearly independent orthogonal matrices span the space of any arbitrary 3 by 3. They are organized according to rotation properties. They're vector-like, tensor-like, or invariant. And here's the really cool thing of this particular choice. They are eigenoperators of RZ. What does that mean? Rotating that tensor around Z will return the same tensor times the scalar. That's fantastic. So there's a whole bunch of rotations we don't even need to do anymore. But when we go to do them, most of them will be Z rotations, and that's just like a scaling factor. The computations have just dwindled. For maximum simplification, we want to not just put sigma as a spherical tensor. We actually want to also write the spin tensor, B0, as a spherical tensor. But you have to think for a minute how you're going to do that. So this is the same thing again. If you want a different way of looking at this decomposition, say somebody gave you a matrix that had arbitrary numbers. They did a QMM calculation and they told you it was this. And they were in some useful basis set, but I mean, they were in some useful coordinate system. But they were in a Cartesian basis set, and this is what they said. They said these 9 numbers, you could rewrite it as a spherical harmonic. It's just a different basis set. And these are the amplitudes. You could imagine writing it as a 1 by 9, and these are the amplitudes of each of those basis 3 by 3s that I showed you before. And the amplitudes are given here. Okay, makes sense? Those are just decomposition into a new basis set. Now, what does it mean to be an eigenoperator of the rotation superoperator? This. I take some matrix, L value and M value specified, not a mixture of them, but just like one of them, one of those 9. And when I rotate that piece of your interaction tensor, you get back exactly the same thing times a phase vector. Now, you can check that. I've given you the 9 Cartesian matrices. You know how to write R. You know how to write a rotation around Z. So you can confirm that those matrices I gave you actually are eigen operators of the rotation superoperator. You can take IZ or you can take IX and you can rotate it if you feel like it. It's not necessarily an assignment for you, but sometimes concretizing these things I'm saying by confirming them helps to make them stick in your brain. So I actually have some examples. I mean, Anna, you're right. There are a few things here that aren't in the notes. Maybe I should just give these to you guys, but promise me you'll try the notes also. Because some of this is sort of sketchy. Without the talking, it might not make that much sense. Okay, so that's a review. So the components organized in terms of the L value are defined by their behavior during rotations. Let me skip that last thing. It might make more sense after this. So spin and spatial coordinates, both spin and spatial terms could be thought of as a second rank tensor and could be written in spherical tensor notation. Does that make sense to you that the B field and the I operators could be second rank? Does that ring a bell for something Art already talked about? So I really belabored the point that the shielding tensor is second rank and defined what that meant over and over again. But B and I thought I was using them as an example of a vector, like that's rank 1, right? Yeah. What we do is we combine B and I into one object by doing something called an outer product. This will be 1 second rank object instead of 2 rank 1 objects. Do you remember outer products? I think Art mentioned them in one of the lectures I was on Zoom for. So if I have 2 vectors and I want to like join them, so it's just one mathematical object, but not lose any information, the ijth element of B outer product I would be BI ij. Make sense? So now I'll have 9 of those. It'll have some sparse properties because there were really only 6 independent pieces of information, and now I've got 9 numbers. But it's nice here to make the spin degrees of freedom and the spatial degrees of freedom be the same kind of mathematical object. It's going to be nice to look at it that way. Just reminding you, when you have 2 matrices, there's lots of different things you can do with them mathematically. You can take outer tensor products. In MATLAB, you would call that prawn. You can take an inner product, like a dot product, like a Frobenius in your dot product. In MATLAB, it's just dot AB, or you're reducing the rank. Here you're increasing the rank. Here you're reducing them. Or you can just multiply them, which, depending on the dimensions, if they were symmetric, you just have the same dimension back. Okay, you can do lots of things with it. Here we're doing the outer product. And outer product is allowing us to write the Hamiltonian in a particularly elegant way. It is the product of 2 rank 2 tensors. They're somehow standing as equivalent peers here. This is a 3 by 3 rank 2. This is also a 3 by 3 rank 2. I asked you as another confirmation exercise, you guys don't pick from these. The ones that seem obvious to you, don't do them. The ones that you're like, is she right? Just do it. That B, a vector, times sigma, a tensor, times I, a vector, will always give you the same thing as making this outer product and then dotting it onto the other one. So in both cases, we know we're ending up with a scalar. This should be a scalar again, no more tensors. But does it really give you the same thing? You can confirm it. Okay. Why I like that, having the spin degrees of freedom and the spatial degrees of freedom look the same in my equation. First of all, there's a kind of like elegance to it. I mean, that just seems cool, but it also has a useful property. If I know that one of these 2, like maybe this one, I'm only supposed to keep one particular spherical tensor component. Like I know I only want the 2, 1, then I only need the 2, 0 or whatever it is from this one. So the tensor decomposition of these, they have to be match, right? Like I take the L equals 0 of this one and multiply it by the L equals 0 of this one. But it wouldn't mean anything. I wouldn't get anything except 0 if I were to take the L equals 0 component of this one and then try multiplying it by the L equals 2 component of that one. It's a basis set and they're orthogonal. So when I write it this way, I know right away that if there's a particular component that's of interest here, I don't need to worry about what the other components were for either of them. And we know we want the isotropic for our offset. We know we never want the L equals 1. So in some cases, it's just not even written in the book, or maybe nobody did the experiment, like maybe we don't even know, because it doesn't matter because it's not going to appear. Or maybe it's just skipped in a book. But there are elements that we always want, which are 0, 0 on both sides, and 2, 0. Because 2, 0 corresponds to L equals 2 ZZ element. We always want that one. So this is the basis set where you can skip everything you don't need. You know exactly what you need, don't calculate anything else. So think about it this way. If I decompose something for the spatial degrees of freedom and something for the spin degrees of freedom, and I had written them out like these 1 by 9s, I only pick up a couple of them. I don't need the rest of them at all. And that kind of operation is written this way. It's a double sum. L goes from 0 to 2, And then M goes from minus L to L. And then I just multiply M with index LM times T with index LM. And I don't do any cross multiplying things. So it's 9 multiplications. It's much less computation than multiplying the rotation matrices, much less. So what are the actual values? This is something I already gave on an earlier slide. What about for the spin operators? What do those look like? I'm giving those to you here, and I think in the handout as well. So T00 is just isotropic shift, like what Art's been writing every week. And T20, oddly enough, looks similar, but is scaled. And some of the other components have other things in them, and we may or may not need them later. When you're talking about CSA, R20 is something we're going to need. R2 plus or minus 1 is something we're not going to need necessarily, but it happens to be 0, and so on. So that's redundant with something we already went over. This is the same question applied to the dipolar coupling. Maybe we'll come back to this later on in the class. And the dipole coupling when it's truncated. Maybe we'll come back to that, but just stay with the chemical shift for now. So the advantages, why do we do this? We can eliminate many pieces that will be 0. We can avoid calculating things we know will never be observable. That's a distinction. Some really strictly are 0. Some aren't 0, but you can't observe them. We don't rotate things that don't need to be rotated. But what do rotations look like in this decomposition? This is a really cool part, and maybe this will be a good place to then stop. So I have something that's in the PAS, some tensor, it's still called that capital N. It has components. So I have to specify L and M, like I'm now going to think about what? L equals 0, M equals 0, okay? And I want to know, how does that look like when I have to rewrite it in the laboratory frame? So I have to rotate it. The usual symbol for rotating spherical tensor is capital D, not R. That's the first thing you notice. And capital D, I want to use the same convention. So first I have to rotate around the z-axis by an angle alpha. That's our rotation, right? But the cool thing is we said, okay, anytime you're doing a z rotation, you just add a phase factor. That's easy. So just calculate what is e to the minus I m, don't forget your m, and alpha. That's it. And the last rotation is around z. E to the minus I m gamma. That should be m prime as written, but I don't think I said that. And that's it. Okay, so those two are really easy. The first and the last rotation is like piece of cake, literally. What about the rotation around y? The rotation around y. Okay, let's think about this for a minute. We are mixing different m values. When I rotate, I do not change an L equals 0 to an L equals 2. That makes no physical sense. But I might have, let's say, m equals +1, and after I rotate, it might be mostly on m equals -1. That's the kind of thing that might happen. Like if you're looking at a p orbital and it was like pz, but now it's px, right? Still p, but. So these are projection factors. How much, if I started out with m, how much of m prime will I end up with? Will not change out, but I will change from m to m prime. How much? How much of m prime? That's d. And d is an explicit function of beta. If beta is 0, then it's delta function m prime. It stays still, right? If the rotation is 90 degrees, it's going to be some interesting number. Like I won't have the same projection after I'm through with the rotation if beta is non-zero. So then these will be some interesting numbers. What are they? You can solve for them, but I'm not going to ask you to do that. They have been determined, and these are the so-called Wigner elements. Like how much is the value of D, how much does m equals 1 become minus m equals minus 1? It's a famous solution. This is just my analogy. Invariant with rotation rotates normally like what we were doing in the plane. Funny rotation. Okay, so if I'm going to rotate something that's L equals 1, and I want to know, it starts out, let's say m was 1. I want to know how much of m equals 1 do I have, how much of m equals 0, and how much of m equals minus 1? Well, the first answer is, well, it depends. What was the angle? But the answer is over here. So how much of 1 is left is this. So that function should be 1 when beta is 0. And then it should get real small when it becomes 90 degrees, right? How much, if I started out at m equals 1, would I convert over into m equals 0? Well, that's this function. Okay? So the resultant will be a linear sum of these 3 states, and these are the coefficients after you rotate. And you just look it up because it's been solved and checked and solved and checked. Let's see, what am I saying at the bottom? The initial state is represented L comma M. After rotation, it is a sum. And the projection factors are these D's that you have to look up here. Note that the rotations around Z are just multiplicative factors of a phase. Rotation around Y by beta makes linear combinations. Coefficient for various elements depends on the angle. Okay, that's all the stuff I said already. So then I have an exercise here. You're going to rotate around Z. I'm sorry, you're going to rotate a vector that represents a Z vector. We're in L equals 1 right now. So we could represent something like a Z vector. You're going to rotate it around Y. But you're going to plug in first 0 degrees, then 90, then 180, and you see if you can just do these manipulations and get an intuitive answer. Okay, that's what these next 3 slides are. And they're more for you to take home. But I gave you a hint here that the Z vector is not 1, 1, and it's not 1, 0, it's not 1 minus 1 in this case. I represented it with the sum of 1, 1 plus 1 minus 1, created a Z vector. So I then have to normalize it, 1 over square root of 2. I could also write it this way. I've got one piece of m equals 1, nothing for m equals 0, and 1. That should be minus sign. So then this should be a minus sign. Yeah, I'm missing a minus sign here. So you have to represent the Z vector in these spherical harmonics, and I chose to represent it by that in that way. Now that you have a representation for it, you can apply those rules for rotating, and you can see what happens when you rotate when beta is 0. Okay, see what happens when you rotate when beta is 0. You're hoping you get the same thing back, right? So check it. And then you can rotate by 180 degrees. And you're hoping that you will get the negative of that thing back. Check it. And then you rotate by 90 degrees and you hope you get something quite different back, right? So you can just play with these, make sure you're comfortable with these. And now you're ready for L equals 2. That's more abstract, but play with L. My recommendation for you, to get this stuff in your brain, if you haven't done this before, play with L equals 1 a little bit. We don't need it for him. This is a piece we're going to throw away. But you'll just feel more comfortable with the nomenclature. It's going to be the same deal, though, with L equals 2. When I rotate something, I've got something initially, and I'm going to rotate it. So somehow I know what alpha, beta, and gamma are, and I know what the initial state is. And if that initial state is m equals 2, it could be some admixture of m equals 2, 1, 0, minus 1, minus 2. These projection factors tell me how much of each, coefficients for each one. But there's lots of alphabet here, and lots of expressions, and this is what you really use in NMR. You use this lookup table all the time. That's how you rotate things. But notice that there's only 5. You can see parts of the simplification already. We had 9 entries when we were Cartesian. Now we only have 5 because we've thrown away parts of that Cartesian matrix. And when we stayed Cartesian, there was no way to throw it away and still use that apparatus. But now we're down to 5. And so here's some things that you can look at. You can try rotating intuitive objects in the L equals 2 also, but don't do that until you've done the L equals 1. You can verify or derive the Wigner elements. You can show that if you express all this in Cartesian coordinates, what is the projection of each of the resultant onto each of those basis matrices. So all of this you can check yourself, and it's so much easier than having to be the person who derived it in the first place. Or you can just accept that it's probably been proofread and use it as it's. Now, let's look at something that simplifies matters. In the lab frame, we always measure along Z. And it also is the case that we always apply the field along Z. So we were talking about in Cartesian that we only need the 3,3 or the ZZ element. Spherical harmonic notation, the selection of that is selecting L equals 2, M equals 0. L equals 2, M equals 0. In this layout, it's right here. And then in the spatial tensor, we don't need to do anything with the L equals 1 or the L equals 2. So we're only going to be working, I'm sorry, we don't have to do anything with L equals 0 or 1. So we're only going to be working with L equals 2. That's clear to everybody? So we're going to learn about that and play with it because it's a warm-up exercise, but we don't do anything with it. We've got a simplification. Now, this is an explanation as to why, if you want to read that, but I think we've already gone over this. In the lab frame, we're only looking for L equals 2, M equals 0. By the way, if you have a uniaxial interaction, so that in the principal axis frame, you also only have the L equals 2, M equals 0 component, like of your CSA. It only has that component. It has nothing else. Uniaxial. Then the rotation through an arbitrary angle beta from the lab frame, or to the lab frame from the principal axis frame. You're starting, you're only interested in this entry in the principal axis. After you rotate, you're only interested in this element in the lab frame. You can derive using these Wigner rotation elements, this famous expression that the projection, when L equals 2, M equals 0, and M prime equals 0, is the second Legendre polynomial. So when we have this big table over here, it corresponds to this one right here. This one right here. So that Legendre polynomial shows up in NMR so much because it is the projection factor of the truncated Hamiltonian on the observable in the laboratory. Truncated CSA, observable, we're just projecting those two elements, and it's here in this table down here. So that's a really famous result. But we need to pick up a few more elements if maybe there is some asymmetry, like eta is not equal to 0. So we can put all that together to write a Hamiltonian. A Hamiltonian will always have a scaling factor to give you some units. And it always just takes matching components in the same frame, both written, for example, in the lab frame, of spin degrees of freedom and spatial degrees of freedom, and just matches those to spherical tensor components. And you can add them all from L equals 0 to L equals 2, and M equals minus L up to L. And you might not need to do all of that, right? You might not need to do the L equals 0 or 1, and you might not even need to do all of the L equals 2. But it always looks like this before it gets simplified. And it always will have the spin degrees of freedom literally in the lab frame, and the spatial degrees of freedom written in the PAS with a rotation slapped on. So they always look like this. And I think the best next thing for us to do when we pick this up tomorrow is to do something like the CSA and work this through a little bit all the way to a spectral frequency. So we'll pick it up from somewhere around this. Calculating the 2-0 component in the lab frame, starting with an arbitrary orientation of the tensor in the PAS frame. These rotations, I think someplace in the handout, there's an exercise to say, let's say you had the simplest possible tensor, uniaxial CSA. It only has delta, it doesn't have A, very simple. And let's say you want to make a measurement and you just have a single rotation. You're just like talking about that goniometer experiment, basically. So you're rotating from the principal axis system to the lab, one rotation, arbitrary angles. You try to calculate that in the Cartesian, and then you try to calculate that in the spherical harmonic, and you do both of them by hand. It's very doable, and it just forces you to go back and wait, what was she talking about? Wait, what does this mean? What's the definition here? How do I do this rotation? And you should get the same answer. And you should have a different number of manipulations that you have to do. One is not that bad, and the other one is like a breeze. If you wanted to do like multiple frame transformations, it might be a waste of your time. But just to do the single, frame transformation. So I've got something that has a non-zero value for delta. You don't have to put in actual values, just put delta. And I have 0 for eta. And I have my rotation matrix, which you can get right out of the handout or out here. And just actually work your way through it. Of all the things that I recommended here, is like, take this home and clarify your understanding. I think this is the best one to actually do. Just rotate and try to predict the observed frequency, Cartesian picture, and then from a spherical harmonic. And I'm pretty sure that'll be early on in what we do tomorrow. And I'm pretty sure it'll make 100 times more sense to you if you just spend 10 minutes tonight taking what we talked about and trying to do it by yourself. Whether you get stuck and give up or whether you actually succeed, either way, it'll make more sense to you. Sound good? Okay. When we have that, we're ready in just like a couple of steps to write the expression for magic angle spinning. We're like so close. Oh, that's funny. What happens when you close the Okay, good. Yes.
Can we actually decompose into symmetric and antisymmetric and only cannot
Say it again.
We are neglecting the antisymmetric part.
Correct. Yes.
So when is it that we cannot?
Or relaxation problems. Do not neglect it for relaxation problems.
And then does it equals to one on this picture?
Yes. It should come into the picture. And if you look through the literature, you can see different people doing different things in that problem. Like, I would not say, it's common to make various approximations and get a relaxation expression. And there's a good reason for it. Maybe they don't have access to the numbers. So maybe they only include the terms where there's an experimentally available value. Maybe they don't have any values for the antisymmetric, so it'll be guesswork, so they leave it out. So you'll see different approaches in the literature. But correct, if you had all the values, let's say from Q1 calculation would be Okay, goodbye.
So that.
Thank you. Nice to meet you guys. Yeah. Bye-bye.